Selamat pagi Bapak. Selamat datang di webinar yang ke-10 dari Prometindo, Asosiasi Profesi Meteorologi Indonesia. Ini merupakan webinar kita yang ke-10. Kita hari ini akan mendengarkan pemateri dari Andrew Bekle dan juga dimoderatori oleh Pak Himawan Tribayu. Mungkin saya bisa serahkan ke Pak Himawan Tribayu. Beliau adalah kepala bidang untuk bidang maaf saya lupa Pak Himawan.
Untuk recycling, ya, bukan kepala bidang tapi untuk recycling, member saja. Okay.
Beliau merupakan dosen di UGM ya, betul Pak Himawan?
Ya,
teknik kimia ya?
Ya, teknik kimia.
Seperti itu. Baik, mungkin saya serahkan waktunya kepada Pak Himawan untuk memimpin jalannya webinar kita hari ini.
Siap, terima kasih
silakan,
sekali Pak Fikri. Ya, terima kasih atas kesempatan yang diberikan pada saya untuk memoderasi session ini. Ini saya mohon maaf sebelumnya akan menggunakan bahasa gado-gado, jadi ada bahasa Inggris, ada bahasa Indonesia. Untuk awalannya, mungkin kalau perkenalan saya tadi sudah diperkenalkan oleh Fikri, saya akan perkenalkan pembicara kita kali ini. So, for this talk, Aptekindo talk, the 10 Aptekindo talk, we are quite we are quite lucky because we have a very prominent talk on extraction. So we have Andrew Bekle. He has experience in mineral processing in related area for more than 15 years. His background is in chemical engineering. As well as chemistry, so it will be beneficial. So if any one of you in this occasion you want to have very broad questions, that will be fine. I do believe that we have a very appropriate person for us, the expert, to talk about the extraction itself. But it is not only his expertise that I quite admire, because Andrew, although he's dealing with mineral processing, because as we know, people always blame mineral processing as a non-environmental friendly process, but his concern on the environment is one of his life value. So he's family man with a concern on environment and sustainability. So not only mineral processing topic that we are going to have here related to solvent extraction, dealing with laterite ores, nickel and cobalt, but we are going also to have the sustainable aspect point of view. So we got everything here. So that's for the introduction. So next, I think I would like to give the time for Andrew to start the talk on the solvent extraction, nickel and cobalt from laterite ore.
Okay. All right. Thank you, everyone. Happy to be here and share some of my knowledge on solvent extraction. And we're going to focus on its use for the recovery of nickel and cobalt from laterite ores. I'll start with a brief overview on Solvay and our mining solutions team, and then talk about the different SX chemistries that can be used for nickel and cobalt separation. I'll then focus on Sinex 272 and cobalt production with that reagent. I'll review a couple of different processing plants and some flow sheets with using the different chemistries, and also talk a little bit about circuit design and modeling. So for those of you who aren't familiar with Solvay, our purpose is we bond people, ideas and elements to reinvent progress. and together we can create a sustainable and shared future. So Solvent is a science company whose technologies bring benefits to many aspects of life. So we have clean green chemistries and also materials. So we're chemicals and materials company. And the group seeks to create sustainable shared value for all. And all of our activities have to fall in under our Solvay One planet, which has 3 pillars, protecting the climate and preserving resources for the future. So Solvay roughly has 23,000 employees and 110 industrial sites, and we're based in 64 countries, so pretty evenly spread around the globe as well. Within the mining industry, if you look at the whole value chain for the mining industry, we tend to focus on the separation step. So we have chemistries that focus on mineral flotation, solvent extraction, which is the business unit that I'm a part of, and alumina refining and industrial minerals. Previously to being called Solvay, we were known as Cytec, and we have a rich history with over 100 years of developments in the industry. All of our offerings tend to align with industry trends and needs. So in terms of improving sustainability, in alumina processing, we have anti-scalants to help reduce CO2 emissions. We want to support global growth for, EV materials, nickel and cobalt, obviously some of them. We want to help our customers do that more efficiently. We're also addressing ore grade decline, so improving the recoveries and selectivities of our reagents so that it improves the profitability and efficiency of mining operations. And then also we're driving productivity improvements with digital initiatives, and one of them is Solve Extract, which is our a digital software that we use to provide real-time feedback to circuits to help optimize their circuit in real time. So enough of Solvay. We'll get into the nitty-gritty of it. So I'll talk now about some of the chemistries that have been used in nickel and cobalt processing. This table shows some of your common extractants that you'll see throughout industry. So we have our acidic extractants and basic extractants, and then within the acidic extractants we have the phosphorus-based ones. So you have Cyanex Deeper, Cyanex 301, Cyanex 272, Vastatic acid, which is a carboxylic acid. We also have phenolic oximes, which are a Corga or licks. And we also have tertiary amines, which are basic extractants. So these are some of the ones that I'm going to go into a bit more detail and talk about today and where they're used. So tertiary amines, these are trialkyl amines, and they're normally a combination of octyl and decyl chain lengths. You can get these from BASF under the Alamine brand name, or Solvay supplies them under the Phentamine brand. Some of the processes that utilize tertiary amines is Falconbridge in Norway, Sumitomo at their facility in Japan, SLN in France, and Vale, New Caledonia at the Goro plant. So the tertiary amines, they require a protonation to start with. So there'll be a protonation step where you protonate the organic and put the acid on there. Then that acid-loaded organic will then extract metal chloride complexes. So the tertiary amines are all used in chloride systems. I guess disadvantages to the tertiary amines is normally, you know, this is in a chloride type system, so you'll have corrosion and you'll need special materials of construction when using this type of system. Vasatic 10 is another common extractant that you'll see used in nickel and cobalt processing of laterites. So the chemistry for this one is C9 to C11 chain length carboxylic acids. And you can get these from Hexion under the Vasatic 10 name, or ExxonMobil also sells a neodecanoic acid. I guess this reagent is good for bulk extraction of cobalt and nickel, and it has a high selectivity against magnesium. So ideal for solutions containing high levels of magnesium in your PLS. Carboxylic acids versus Sinex 272 and the other phosphorus-based extractants, the selectivity order is reversed. So it'll actually pull nickel before cobalt, whereas all of the other phosphorus-based extractants will pull cobalt first before nickel. And much higher selectivity for cobalt and nickel relative to magnesium than the other extractants. Also, the range at where you're extracting the cobalt and nickel is a lot higher with Vasatic 10. So it's in that sort of neutral range of 7 to 8 is where you're going to be doing your extractions. You have quite high aqueous losses of the extractant. So typically in a circuit with the Vasatic 10, you're going to need a special stage at the end, which acidifies the raffinate to try and recover some of your extractant losses. Phenolic oximes is another type of extractant that we'll see in nickel and cobalt. BASF will supply these under the Lix branding. Solvay has Acorga, and Halochem has Mextrel. You'll see phenolic oximes used in ammonia-based systems. And the processes where that's used is the MHP ammonia releach type systems. Queensland Nickel, Coors and Bulong all used phenolic oximes as well in their circuit flow sheets. The extraction follows, you'll extract the nickel as either a tetraamine or a hexaamine complex. And when the extraction, when you extract the nickel, you will also form ammonia and ammonium as a byproduct of extracting the nickel. The equilibrium reaction can be driven in either direction, depending on the relative concentrations of the species there. Disadvantages to oximes, cobalt can be an issue. So when you extract cobalt-2, it can oxidize to cobalt-3 and form a cobalt-3 complex on the oxime, and that will not strip off under the normal stripping conditions that you'll strip your nickel under. So therefore it builds up on the organic, tying up your oxime, and it requires a regenerative strip process where you do a reductive strip to remove the cobalt. So also the other main type of extractants are your phosphorus-based ones. They all use a cation exchange mechanism where 2 moles of extractant will extract any of your 2+ valence metals, and you will generate some 2 hydronium ions. There's deeper, Sinex 272 and Sinex 801, or also known as Ironquest 801. They're the 3 main ones. And you can see their S curves displayed here. So Sinex 272 will exhibit the highest selectivity for cobalt over magnesium and calcium and nickel. So you get the largest amount of cobalt nickel selectivity from Sinex 272, and the order decreases with your phosphinic, then your phosphonic, which is the 801, and then the phosphoric, which is your deeper. That's also relates to the order of acid strength. So deeper is your most is the strongest I guess acid, and you'll see that all of the, generally speaking, a lot of the metals will extract in a similar order, but if you look at the iron, and the pH at which it extracts, you'll see it's the lowest with deeper, in the middle with the 801, and then with 272 it's slightly higher. So that gives you a bit of a comparison there, and also the strength at which the extraction happens. So deeper will be the strongest, and with iron, for example, deeper will require 6 normal HCl to strip iron off. The 801 is in the middle, and you need 400 gram per litre sulfuric to strip iron, and then Sinex will strip the iron off at 150 to 200 gram per litre sulfuric. So in certain circumstances, the stronger acids extractants are more advantageous, and in other situations they're not, depending on the metals that are present in your feed and what your objectives are. Sinex 301 is the last of the phosphorus-based extractants that I'm going to talk about today. I won't spend much time on it. It's no longer commercially available, but you'll probably see it a lot in the literature when you're looking at SX and nickel cobalt extraction. It was part of the Goro flow sheet at Vale's New Caledonia operation. Technically, the reagent was a really good reagent, and it was used to selectively extract nickel and cobalt away from magnesium and calcium. And it did that very well. However, it had some limitations as well regarding the stability of the reagent. So the reagent would readily degrade and break down, which ultimately affected the economics of using Sinex 301, and there are no other commercial operations using 301 at the moment. So Sinex 272, I'll focus a little bit on that. This is our main extractant used for nickel and cobalt. So in your ores, typically cobalt occurs with copper and nickel at relatively low concentrations, and the cobalt's one of the byproducts of leaching your nickel. Sinex 272 was specifically designed to separate your cobalt from your nickel in a weakly acidic solution. It's also used in other applications. Some plants use it for iron and zinc removal, and it's also used in the separation of heavy rare earths as well. This is the S curves, so the order of selectivity in which Sinex 272 will extract metals. So when you're looking at these S curves here, the order of preference or order of selectivity will be the order in which the reagent will preferentially extract metals. So for example, if you had all of these metals in solution and the pH was roughly 4, you would extract everything to the left of pH 4. So you'll extract your zinc, your copper, some of your manganese, and some of your cobalt and magnesium. Also, when you're looking at these S curves, they give you a general metal selectivity order. They're created under ideal conditions. So they'll generate these S curves using single metal solutions with low metal concentrations and large excess of ligand, and you'll generate these nice curves. When you have multi-metal systems with different concentrations, they can move around slightly. So it's you always need to, I guess, do the testing using your conditions. But you can get a general guideline from these curves, and it gives you the order of extraction. Some of the main properties that you need to be aware of when you're looking at Sinex 272 and other SX systems for that matter is solubility level. Sinex 272, the aqueous solubility increases above pH 5. You can see that the aqueous solubility goes from 8 to 25. It's also a function of the salt concentration. So in your circuit to, make sure that your extractant stays in the organic phase, high salt concentration is good. You don't want to go too high in your pH, and you should be okay. Also, when you're doing calculations, we always want to calculate the moles of phosphinic acid and the stoichiometric loading so that we can calculate how much metal is loaded onto the ligand. So you can get the purity, the specific gravity, and the molecular weight as well from the data sheets. Cobalt extraction with 272 occurs via the cation exchange mechanism. So 2 moles of extractant will extract 1 mole of a divalent cation, and you'll form the ligand complex or the metal complex there, organometal complex, and you'll generate 2 moles of hydronium ions. So you'll be generating acid. So to drive the extraction equation, we want to reduce the acid levels. So we want to add base to promote extraction, and then to remove the metals back off the organic, we want to increase the acid to promote stripping. The extraction kinetics are pretty quick with Sinex 272, so you'll see 90% equilibrium after 60 seconds. Organic phase viscosity control. So one thing that you have to be aware of when you're operating a solvent extraction plant, typically as well with your phosphorus-based extractants, is you want to be aware of the viscosity of the organic to make sure that you get good phase separation between your aqueous phase and your organic phase. And there's 2 factors that will influence your viscosity. The first one is your extractant concentration. So the higher the volume percent of extractant you have, the more viscous the organic phase will be. And also the metal loading. And with Sinex 272, we like to calculate the amount of or the percent metal loaded onto your ligand. If over 70% of the ligand is, well, it's about 75% of the ligand is loaded with metal, you get a exponential increase in the viscosity of the organic. You can form gels, emulsions, and it's basically the stoichiometry of the organometal complex changes, and you get a polymerization type reaction occurring, and that's why you start it goes really viscous. So for an operating circuit, you can lose your organic, and it's critical to stay below. We recommend operating in that 60 to 65% loading range. So I've mentioned it before, the addition of base. If anyone's familiar with copper solvent extraction, which is probably the dominant metal extracted with solvent extraction, the oximes are really strong extractants, and the extraction occurs below pH 2. So if you take, for example, a feed with 1 gram per liter of copper in it, when you extract that 1 gram of copper, you're going to generate 1.54 grams per liter of acid. And if your PLS is at a starting pH of 1, you'll generate 1.54 grams of acid. Roughly you'll move to pH 0.9. And, if you look at the S curves, that's okay. And you'll drive that extraction all the way, and you don't need to worry about it adding any base. However, with a cobalt extraction, that's happening at weakly acidic conditions. So the addition of base is required to maintain the pH in the region where extraction occurs. So if you do that same calculation, extracting 1 gram per liter of cobalt, or 1 mole of cobalt, and generating 2 moles of your hydronium ions, and you start at a pH of 5, you'll easily the pH will drop quite quickly and limit that reaction from proceeding. There's 2 main ways in that we'll add base to solvent extraction systems here. The first one is interstage pH control, where you will add the base directly into the mixer where the organic and the aqueous are coming together. And typically plants will do that so that they can run a pH profile down their extraction train and target different pHs. The second option is salt conversion or pre-neutralization, where the organic is contacted with a strong basic solution, and then the aqueous is removed, and that organic, you will, like if you contact the organic with a sodium hydroxide, for example, you will load sodium onto the organic, and then when you contact that sodium loaded organic with your PLS stream, the sodium will be exchanged for cobalt on the organic. Most plants will use a combination of the 2 methods, and you can use any base you want, sodium hydroxide, ammonia. Generally, it comes down to what's readily available and economic in the area. You also have to take into account you will form, for example, with sodium, you'll form a lot of sodium sulfate as a byproduct, and you need to be able to get rid of that. Whereas with ammonia, you'll form ammonium sulfate as a byproduct. And murrin, for example, crystallizes the ammonium sulfate byproduct and sells that into the fertilizer industry. Whereas sodium sulfate can be difficult to sell as a product or dispose of. So I'll talk now a little bit about cobalt production with Sinex 272 and what a typical circuit will look like. So we'll have three main bits to a solvent extraction circuit. We have our extraction stage, our scrubbing, where we'll try and remove any impurities off the organic, and then a stripping stage. So in this example circuit that we'll look at, there's cobalt, magnesium, and nickel mainly in the feed. We want to recover over 99% of the cobalt, and we want to reject the magnesium and the nickel. So extraction, typically in commercial circuits, you'll have 3 to 6 stages here. The pH is highest in the stage where the raffinate exits, and it's lowest where the organic exits. And you can control the pH as said by pre-neutralization, mixed box pH, or a combination of the two. So most plants will use a combination of the two. Scrubbing, once again, we see 2 to 5 stages. Now that there's the trend towards EV batteries, we're seeing more scrubbing stages being put in as the purity levels in nickel and cobalt salts for batteries are very tight. We're seeing more scrub stages being put in to achieve those purity targets. And some of those more higher purity circuits, it's common to see cobalt recycles up to about 30%. The more scrub stages you have, the lower that recycle number can be as well. So there's a trade-off between having higher capital with more scrubbing stages versus lower operating costs down the line with a reduced recycle. Stripping, typically 2 to 4 stages in a commercial circuit. The cobalt is stripped quantitatively from the Sinex, so it's different to your copper circuits where you have a recirculating load of copper going around. The stripping can even be done in one stage if you have sufficiently low pH or an excess of acid. Normally, the multiple stages are used so that you end up with less free acid in your final product, and it's a more efficient use of your acid. And it's easy to achieve cobalt concentrations from 110 to 120 gram per litre. There's two sort of mechanisms that you can use to scrub the impurities off the loaded organic. So when you load the organic, you're going to get a little bit of magnesium and a little bit of nickel extracted with your cobalt, because you're wanting to extract all of the cobalt. A little bit will come with it. Now, to remove those impurities, you can either use metal-metal exchange, which means you will use a scrub solution containing cobalt. This can also be called the crowding effect. The extractant will preferentially want to load cobalt over magnesium and nickel. So if you have a solution with an excess of cobalt there, it will exchange the magnesium and nickel on the organic for that cobalt that's around. So we'll see, depending on your downstream processing, for example, if you have an EW circuit, you may need to bleed from the EW due to some impurities in your EW, and you will have a rich cobalt solution, and that will be ideal to use for scrubbing. The spent scrub will go back to the PLS, so it's not lost, but it is a recycle. Selective stripping is probably our preferred method, where basically it's the same mechanism as stripping off the organic, but we'll use a weak acidic solution, or not a strong acid, and we'll basically gently strip off the metals, and it'll preferentially strip the magnesium and the nickel first. There's benefits to this in terms of reducing that cobalt recycle in the system, and we can achieve similar selectivity and similar purities at the end. So we're seeing more plants move towards that, whereas more of your older plants traditionally used a metal-metal exchange mechanism. So when you tie all of these things together, what you're looking at here is the full circuit, and we can see that in the PLS here we had our 3 grams of cobalt, our 5 grams of magnesium, and our 90 gram per litre of nickel. You can see the spent scrub will come back in and alter the feed. So the feed is actually a 3.48 cobalt, 5 magnesium, and 87 of your nickel. We're adding 52% pre-neutralization of the ligand in the pre-neutralization tank here, and then they're letting the pH swing across the extraction stages. You can see the cobalt magnesium ratio in your feed here is 0.6, and we'll see how that upgrades to 17 on your loaded organic. And then after scrubbing, we'll see that the scrubbed organic has 2.9 gram per litre of cobalt, and we've taken the magnesium down to 0.9 milligrams, and the nickel has been completely removed. So in your rich liquor, your cobalt to magnesium ratio is 3,284, and there's no nickel present there. In terms of I guess looking and developing and operating these circuits, Solvay developed the MinChem modeling software to assist with basically the design of the plant, and also operating and improving an existing circuit. So our objective when we developed the MinChem modeling software was to assist in the design of circuits. So we wanted to, determine the operating conditions required. So for the optimal selectivity of your metals against the impurity metals, how many stages to put in, your concentrations, your O to A ratios, and your pH profiles. And then the outcome from using the software is basically we can assist you to reduce the size and complexity of bench scale test work programs. So we can model a circuit based on the PLS and put you in the starting range and save you some time there. We can also give you increased confidence in your chosen circuit design and improved understanding of how it works. So basically, if you've come up with a circuit and you've done the lab work and designed a circuit, we can basically model the PLS and use those circuit conditions and confirm that that circuit design will behave how you've predicted it to behave. So we can give you increased confidence there. Also, we can help to reduce the operating costs of an existing circuit by maximizing the reagent and the plant performance. So an example of how that can work is this is I guess a scenario with an operating plant using 3 stages of extraction here, and you can see we've modeled lots of different pH profiles across the 3 extraction stages. Your cobalt recovery is the little blue dots. So ideally we want to see high cobalt recovery. So we want to be up in the region where that cobalt recovery is flatlined, and we don't want to load very much magnesium and nickel, which is your red and your green squares down there. So we want to be up in that range there with the high pH in E2, E3. And we want to have a low pH in the first extract stage to try and reduce the amount of impurities that we load. So we get a nice profile from low to high across the extraction stages. How do we apply this as well to circuit design? So this is an example where we've compared using 2 stages, 3 stages, and 4 stages of extraction at multiple pre-neutralization amounts, and seeing what the results come out like. So for this circuit, with the PLS with your 3 grams per liter of cobalt, the minimum amount of base required to extract 100% of the cobalt was 0.1 mole per liter of base, which was equivalent to 38% pre-neutralization. So that's the lowest amount that you could use. We always see a little bit higher because you extract some impurity metals with it. So you can see here, when you look at your cobalt recoveries, with 2 stages, you needed to go to 50% pre-neutralization to get up to 99% cobalt recovery. But then your cobalt magnesium selectivity was 8, and your cobalt nickel selectivity was 42. If you increase to 3 stages, you get 99% cobalt recovery in with a lower amount of base. So you're only using 45% pre-neutralization. So you're more efficient with your base, and your recovery is slightly higher. Your selectivity is also greater. So your cobalt magnesium selectivity has gone to 14 and 70. So that means as well, in your scrubbing stages, you won't have to scrub as much off, and you will have a lower recycle and lower operating costs associated with that as well. Now, if we go to 4 stages, you can see that same amount of pre-neutralization, 45%, we went from 99.8% recovery to over 99.9%. And our selectivity basically stayed the same. So you'd say, looking at this data, 3 stages would be optimum for this circuit configuration. We can do a similar thing for scrubbing as well. So we can look at the impact of increasing the scrub stages from 2 to 3 to 4. And we've fixed the amount of cobalt recycle at 20% for the purpose of this work. So you can see all of them had the same loaded organic composition, and then the scrubbed organic, the amount of cobalt remaining is the same. So we targeted the fixed recycle, but then you want to see the impact on what happens to the amount of magnesium and nickel left on there. You can see that with 2 stages, with all of them, you've removed the nickel easily. However, to get the magnesium down, 2 stages, you've got 4 milligrams, and then with 3, it goes to 1 and 4.3. So it's, diminishing returns as you increase the stages, but it depends on what sort of purity you want in your final product. All right, so I'll take some time now to go through a couple of example nickel and cobalt laterite flow sheets. And basically, I was going to go over a couple of different ones, touching on ammonia, sulfate, and chloride type systems. So the first one is Queensland nickel, which is an ammonia-based system. This plant was commissioned in 1989, and the plant closed in 2016, and had a capacity of 32,000 tonnes per annum of nickel and 14,000 tonnes per annum of cobalt. They were sourcing their laterites from New Caledonia, and the leach process was the Karen process to treat the ores. So it was an ammoniacal leach. There was a roasting to reduce the nickel and cobalt to their metallic forms, and then the metals were leached in to an ammoniacal solution. Your nickel is separated from your cobalt using LIX 84, so your oxime system, and then your nickel is stripped off by the nickel is then precipitated as a carbonate, and then from that precipitation, the nickel is reduced by with a hydrogen reduction to form nickel powder from the nickel carbonate. The raffinate from that nickel extraction with the LIX 84 goes to the cobalt plant, where the cobalt is precipitated into a sulfide. Then is re-leached. Sinex 272 was then used to remove the iron and the zinc away from your copper, nickel, cobalt, manganese, calcium, and magnesium. And then deeper was used to extract all of your valuable metals out of the sulfate media and then stripped back into a ammonia media. LIX 84 was used again to remove any residual nickel, and the same sort of hydrogen reduction process was used to make nickel powder. And then ion exchange was used to clean up calcium, magnesium, and you ended up with the pure cobalt stream. Bulong was one of the first sort of HPAL operations in Western Australia. There were three of them. There was Coors, Bulong, and Murrin. So Bulong operated a plant 30 kilometres east of Kalgoorlie, treating laterites with the high pressure acid leach. It was interesting in the fact that it was the only plant to be treating using a direct solvent extraction at that time. So it meant there was no need for precipitating an intermediate product for that concentrating step after leaching. Your copper, cobalt, zinc, and manganese was separated away from your nickel, calcium, magnesium with Sinex 272 in this first step, which was your cobalt SX step. And then there was a selective precipitation, and that went off to your cobalt refinery. The cobalt raffinate went on to nickel SX, where basically the zinc was removed with deeper, and the cobalt was then recovered by the nickel was recovered by EW. also in that Bulong circuit, the nickel SX step was done using vasatic acid, and yeah, the zinc was cleaned up with deeper, and copper cleaned up by ion exchange. Murrin was the third one of the West Australian HPAL plants, started in the 1990s. I've summarized, or in the table below, there's a summary of the 3 HPAL plants that were all started in the 1990s. Murrin is the only one still operating. You know, in these sort of first generation HPAL plants, they had a lot of troubles in terms of maintenance and scaling, and basically wear and tear on the equipment. So you know, in Bulong, that was a lot of the issues that they had. They also had a lot of calcium scaling happening and through the system. So but the Murrin circuit still operates today. I guess their flow sheet is similar. Well, it's got the high pressure acid leach, and then CCDs we use for your solid liquid separation. There was some neutralization for ion removal, and then there was H2S added, so a nickel cobalt, a mixed sulfide product was produced, and then basically that's where your magnesium, calcium, and manganese is removed, and then there's a POX extraction to re-leach your mixed sulfides, and that's with the re-leaching, the iron and aluminium is precipitated and removed there, along with your copper, zinc, and that's recycled back to the front of the process. In terms of SX, they have 2 solvent extraction circuits. The first one, both are with Sinex 272. The first circuit removes zinc, and then the second circuit extracts the cobalt away from the nickel. They use hydrogen reduction in both the nickel and cobalt product streams to produce nickel and cobalt briquettes. The final the flow sheet we have to look at today is the Eramet's SLN plant, which is a chloride process. So Eramet has their Le Havre Sandeville refinery, and that's in France, and they process a matte produced from its laterite smelting operation in Doniambo in New Caledonia. So the smelter in New Caledonia is fed with a laterite ore that's rich in the garnierite. Didn't say that very well. And basically there's a calcining step, and then your electric melting to produce your a ferro nickel, and then that is further refined into your matte by a sulfurization step to help remove the iron. So the matte is then loaded onto ships and sent to the plant in France for further refining. They leach the matte in using chloride conditions, and then that's fed to a solvent extraction circuit. So the first solvent extraction circuit is to remove your iron, and they utilize TBP for that. And then they use tertiary amines to extract your cobalt away from your nickel, and they make a cobalt chloride product. And then the raffinate from that SX goes to electrolysis to purify the nickel, and they make either a nickel cathode or a nickel chloride product as well. All right, thank you. That's all of my slides for today. Please let me know if you have any questions.
Yeah, thank you, Andrew. It is indeed nice talk, and some of the information are very insightful. I think the participants are a little bit timid, so we have only one question at the moment, Andrew. But I do believe that there will be more to come. So I would like to convey a question from Arifo. Actually, you have already presented the process, because according to the talk that you've done, according to the real process, there are two types of process, right? After the solvent extraction, you have electro winning as well as precipitation. So resembling to what Arifo question is that, how could you determine which one is which efficient for the process that you would like to apply for your ore or processing after the solvent extraction? Because you have two types, right? Precipitation, and then you have also electrowinning. So which one is which?
Yeah, well, I guess yeah, there's a couple of options there. It comes down to market demand, what you want to produce. So, you know, also it comes down to availability of electricity. So I guess if you're running like a nickel EW circuit, that can be energy intensive. So it'll come down to energy availability if you're using grid power versus generating your own power. In terms of, you know, we're seeing the trend in the industry move towards, you know, nickel and cobalt salts for EV batteries. So that's sort of driving the end product, where instead of going to an EW circuit, it's feeding a crystallizer, and they're making those the nickel salts. That's being driven by a premium that the customers are seeing for those products, and that's driving the choices in what downstream option they use after solvent extraction. So,
okay, thank you, Andrew. Hopefully it will answer Arif's questions. And it's getting warmer, it's getting hotter, because when we talk about nickel, it will be one of the biggest resources in Indonesia. So we have one participant who would like to direct a question to you. So please, Pak Indra Perdana from Gajah Mada University, he has already raised his hand. So I would like to, please have your time.
Thank you very much, Dr. Bayu. Good afternoon, everybody. Dr. Andrew, thank you very much for your nice presentation this afternoon. It's very nice to see what is the benefit to use solvent extraction to separate metals, especially cobalt from nickel. Yeah. And I have questions. Actually, I have several questions, but I would like to ask one question first. You are talking about the separation of cobalt from nickel and other metals, using solvent extraction. Especially you mentioned about using cyanide 272. I'm just thinking about, as you already mentioned in your previous slides, you mentioned about how the S curve that you are developing that use single component extraction, something like that. And I'm thinking if we are going to use that for multi-components, as already mentioned by in your presentation. And if we have quite wide range of concentration. So I would like to ask you, is there any limitation how wide of the concentration that can be handled by this solvent extraction? Because sometimes we have some metals that have quite high concentration, and the other they have quite low concentration. Thank you.
Yeah. So I guess solvent extraction can handle a wide range of concentrations. You can alter the reagent strength, so the volume percent of the active within the organic. And then also you can alter the organic to aqueous ratio in your extract. So if you want to extract a large amount of metals from your aqueous phase, you can use a high O to A ratio in extract, and also a higher concentration of the reagent. Coming back to the first bit of your question about the S-curves and the fact that they move when you have a multi-metal system, that's correct. I mean, we develop for the brochure the S-curves with single metals to give you an idea of how the reagents will behave, and it gives you a guideline and a starting point. If you have a really high concentration of one metal and a really low concentration of the other, and you're trying to pull away the metal with the low concentration, there is a driving force from the other one. It will want to load onto the organic as well. So yeah, it does have an impact, and that's why it's critical to do test work when you're developing these systems, just because a staging configuration worked on one plant for their conditions doesn't necessarily mean that it'll work for the conditions of another plant. So it's critical to do some laboratory work to confirm the conditions. We can also assist with modeling to help with the staging and conditions as well.
Indra, is there any further comment or further question? I think he's cut off. Yeah.
Hello.
Are there any questions from other participants?
Hello?
Pak Indra, yeah, already connected. Any further question or comment, Pak Indra?
Yeah. Yes. Thank you very much. Sorry, I forgot to introduce myself. Actually, my name is Indra Perdana from Mineral Processing UGM. One more question, Dr. Bayu. Dr. Andrew actually also described about the models he also developed from this region, yeah. And I'm just thinking about, from the model we can then determine or predict how many stages that we are going to use to extract certain metals. But I'm just thinking, is this model based only on the equilibrium, or is it also there is also concern about the kinetics? So we can also use the models to estimate the size of the equipment.
So the model is for the equilibrium of the metals. So it's not for the sizing of the equipment. The model makes some assumptions like you're going to have 100% stage efficiency within your mixes. So it's assuming that your equipment is designed correctly and has efficient mixing. The model, we have various conditions, so we can model at different temperatures. So the selectivity in the S-curves will move from work being done at 25 degrees in the lab versus 50 degrees on a plant. So we will recommend that Synex 272 circuits are operated at 50 degrees C because you see a benefit of increased selectivity at that temperature. also typically after leaching, that's a normal temperature that we see as well in the circuit. So that's something also that you need to take into account when you're doing lab work, that you will get better selectivity at those higher temperatures. Yeah, does that answer your question?
Yes, it is. Yeah. Thank you very much.
Oh, sorry.
Okay,
one other thing. Also, the model basically it's based off. We do a lot of multi-metal systems, so there's a lot of lab work involved to develop the model, and they do a lot of metal distribution curves over a wide range of conditions, and then we've basically confirmed the model with a pilot against piloting as well to verify the model.
Yeah. Thank you, Indra, for the question.
Okay, thank you very much.
Yeah, a little bit further, Andrew, because we come up into the model, and you mentioned that the model is based on the equilibrium. So does it mean that you have also certain residence times that you've set into the model? Yeah.
So as I said, we assume 95% stage efficiency for each stage. So a typical design of a Sinex circuit will have 5 to 6 minutes in residence time in your mixers, that sort of thing, or 3 to 5, somewhere in there. And we know that at temperature you get 90% extraction happen after 60 seconds. So yeah, the model does also assume complete stage efficiency. So I think when we were doing the lab work to justify the model, I think they used 15 minutes as the mixing time for each of the stages.
Okay, will it be the same in terms of the solvent extraction as well as the scrub? Will it be the same, the residence times that you've set into the model, or will it be different?
That's the same.
Yeah. Okay. Yeah. Thank you, Andrew. Is there any other questions or comment from the participants? Because it will be hot issues related to nickel, and we are into the electric vehicles in the near future, so nickel will be important. So is there any participant from the industry or practitioner at which you would like to convey some practical consideration? Oh yeah, we have one, Pak Eric Prasetyo Zen. So please convey your question. You haven't unmute your mic.
Thank you, Mr. Bay. Okay, Mr. Andrew, my question is simple. The pressure disengagement is one of important parameters in solvent extraction. My question is, what is typical normal phase disengagement in the industrial scale? That's all.
So normally it gets designed for the specific system. Not all phases will separate at the same rate, but typically I think it's you're looking at about 6 minutes sort of residence time in the settler to get nice separation in the settler. In terms of when you're doing the lab work, you'll see the phases break within 30 to 60 seconds.
Yes.
You'll get complete separation of the phases. One of the things that you need to be aware of with a solvent extraction circuit is that because the organic is being recycled around, you need to take care of we call it the health of the organic. And you need to be aware of, certain things will impact it, like colloidal silica, for instance. So that's one of the things that will come and go in the leach. Colloidal silica can form gels and emulsions, and it just won't separate in the plant. So you can run, there's aqueous continuous and organic continuous in your settlers. There's levers that you can pull to help mitigate the impacts of some of those things. Another thing that will impact your phase disengagement time is if you're in your upstream processes, like flocculants and coagulants, you have to be careful in your selection of those materials. If you over flocculate, that can negatively impact the solvent extraction circuit. You know, it's interfacially active, so it will interfere at that aqueous organic boundary and slow down the separation time. So it's important to do that. For example, as well, in like a copper SX circuit, they will have clay treating as a step to remove those interfacially active impurities that build up in the organic to help improve the phase separation time again. Which, yeah.
Okay. May I ask again, Mr. Bayu, is it fine?
Yes, please.
Okay.
Take your time. Yep.
I also noticed that phase in disengagement also are affected by the pH of the PLS. Yeah, usually the increasing pH causing the, you know, like saponification things. And do you have any suggestion about that?
So is that in terms of like in your extraction stage?
To improve the phase in disengagement in the more alkaline or neutral pH.
Yeah, so I guess the higher the ionic strength, a larger ionic strength will help the phase separation as well. But yeah, you will start to see that if you go towards those neutral pHs and have low ionic strength, you will have a slower separation. So
so you suggest we can add some salts into our aqueous phase,
like for
to
example,
increase the ionic strength.
For example, if you know, you're pulling the cobalt away from the nickel, if you can maintain a higher nickel tenor in that solution, that will help with the phase disengagement. Whereas if you're pulling all of the cobalt away and you have a low nickel tenor, you know, that's what I'm meaning by that, like increasing the other metals that are there, so that will help the system.
Okay, thank you, Andrew. Thank you. What about you?
Thank you, Baidek. You haven't introduced yourself. From which institution
actually we my name is Eric Prasetya. I already contacted Andrew before last year.
Okay.
Asking for samples. I'm working from LIPI, Indonesian Institute of Science. Thank you.
Okay, Andrew. Thank you. It's very insightful. I mean it. So I'm a little bit curious because you mentioned about the previous step before, and as we know, when we are dealing, I don't know the limitation because the limitation is not yet there, but bioleaching or bio application into mineral extraction is increasing due to the limitation of the concentration of minerals in the ore, as well as due to the sustainable development issues. In that case, when we apply bioleaching, because in bioleaching usually we are dealing with the organic acids, right? Will this technology can be applied, or is there any limitation? Because you mentioned before about the reagent of flocculant agent, etc., that will affect this extraction process. So what about the bioleaching acid, organic acid? There.
Well, I guess I haven't sort of seen too many instances of that in nickel and cobalt. One plant springs to mind, which is Terrafame in Finland. So they have the heap leaching of a low grade nickel copper sulfide ore there. They have the heap leach there, and it is a bio heap leach. However, then they have an intermediate step where they precipitate all the metals out with basically H2S. So they do the mixed sulfide precipitation, and then they have epox to re-leach the metals before solvent extraction. So there's a lot of treating in between the heap leaching and solvent extraction, where I don't think that the bugs or the bio leaching would survive those intermediate processing. Saying that though, on the copper side, it is common to see some bioactivity in copper heap leaching, and you know, the copper heap leach SXEW type system, those leach liquors are going straight into a solvent extraction plant. And I haven't heard of any negative effects due to it. Yeah. Okay.
Yep. Thanks for the information. Any other questions from the participants? Anyone? It will be very interesting topics. So please, yeah, and it's practical. It's not research based. If I talk about research based, maybe it will be a little bit boring, but yeah, it's practical. So please convey your doubt or your considerant, because we have Andrew here. Before the participant, maybe Andrew, I would like to ask a question, especially when we are trying to develop the reagent itself for the extraction, because you mentioned about the functional groups, right? Like phosphanolic, carboxylic acid there. In terms of, because the mechanism is different. At the beginning, I thought the mechanism, it will be the same with the bioleaching, because in the bioleaching we have the complexation. So we have complex metal with the organic compound there, and usually it will be affected by the existence of the functional groups in the chemicals. While in this case, the functional, you have only one, but you have a long chain of carbon there. But the functional groups, it is only one. So based on your experiences, which part will affect the selectivity of this reagent to the solvent extraction? Because you only have one functional. Is it the carbon, the long chain carbon, or anything?
I'm actually not too sure on that one. That would probably be a question best suited to some of our R&D folk.
Yep.
But yeah, I guess you want something that's able to bridge that. You know, it needs to be organic soluble, yet it needs to interact at the interface there with the aqueous as well. So yeah, you want that long chain, yet you want I guess either that like acid type side to it as well. So in terms of what makes a good extractant, yeah, that's a difficult one. And as you see, like Sinex 301, that on paper was a really good extraction, and technically it performed very well. However, it wasn't stable. So you need to weigh up all of those things when developing these new molecules. You want it to be selective, you want it to be stable, and you want it to be a reasonable price to manufacture as well. Yeah.
Okay, we are still waiting for many questions to come. Is there, or are there some questions? From my point a few, Andrew. Maybe it will be practical because you also put alkaline, right? You put a base when you try to adjust the pH because of the pH drop during the operation. But in the other side, for the characteristic of the extractant itself, the solubility will be also affected, not by the pH, but also by the salt concentration. So how could you balance that? Is there any tips or tricks? Aside from the concentration of metals itself, the initial metals concentrations in the feed.
Yeah, so I guess as well, like when you're adding the base, so particularly when like talking with Sinex 272, the sodium salt of the Sinex. So when you do the pre-neutralization and you're adding sodium to it, we recommend that you don't exceed 50% pre-neutralization there, and that is due to after that point you end up with really high aqueous solubility of your extractant, and you will lose it all. So you know, you can load more metal on, and that's why plants will have a combination of pre-neutralization and adding additional base through the mixes. So it depends on which metal it is, will determine, you know, they each have different aqueous solubilities as well, and limits at which the solubility starts to become an issue. So it's very dependent on the metal involved. Yeah.
Okay. Yep. Thank you, Andrew. Are there any questions? If there is no question, then I think thank you very much, Andrew. It is indeed a nice talk for me, especially because I'm not into a solvent extraction person, because my background is on flotation, and now I'm doing on anything that I can do related on minerals. Yep. So thank you very much for your time. Thank you very much for the talk. And I do hope that you would not be mind if there is a further question, or there are some questions aside from this event that will be asked by all the participants here. Again, thank you very much, Andrew, for your time. And I would like to give it back to Fikri.
No worries. Thank you very much. It was a pleasure.
Thank you very much.
Mr. Andrew and Himawan. Before we close the webinar, how about we have a photo documentation session first? If you don't mind, please turn on your video. Bapak dan Ibu sekalian, mohon bisa dinyalakan videonya. Kita akan coba ambil sesi dokumentasi. Di saya masih ada beberapa yang belum nyala. Sembari menunggu sebentar. Oh ya, untuk link materi nanti akan disampaikan di grup WhatsApp mungkin ya, biar bisa di-share ke semuanya sekaligus. Untuk slide yang pertama, saya ambil dulu. 1, 2, 3. Sekali lagi, 1, 2, 3. Oke, untuk slide kedua. Satu, dua, tiga. Dan slide ketiga, the last slide. 1, 2, 3. Baik, terima kasih Bapak dan Ibu sekalian. Mungkin dari Pak Hanafi sebelumnya, ada yang mau disampaikan dulu?
Okay, hi. Thank you, Andrew, for this occasion. Yeah, you present very well. And before that, we chat in emails that you meet the time. and thank you for that sharing. Probably next time when we have another webinar, we will call you probably sometimes next year in the first quarter. I hope you will interest to join again. Yeah, Andrew. And we hope that you very well, good, stay healthy from this pandemic. Okay, that's all. Thank you, thank you, Andrew, and thank you for the committee and moderator, Pak Bayu. Yeah, thank you very much.
Oke, terima kasih Pak Nafi. Mungkin itu saja dari kami. Akan bertemu lagi 2 minggu lagi, Bapak dan Ibu sekalian. Untuk 2 minggu lagi, sebentar, saya cek dulu materinya. Dua minggu lagi kita akan bertemu dengan Bapak Fabian Imanasa Azov. Beliau merupakan PhD di Norwegian University of Science and Technology. Materi yang akan disampaikan adalah proses produksi alumina menggunakan proses Pedersen untuk mengatasi dampak lingkungan dan meningkatkan nilai guna lumpur merah di Indonesia. Itu tanggal 12 Agustus 2021 di jam yang sama seperti biasa, pukul 30. Terima kasih Bapak dan Ibu sekalian atas kehadirannya.
And
Semoga
Fikri, don't forget, Andrew, we also have certificate for you for this webinar as a speaker.
All right.
Yeah, we will send email to you. Thank you.
Yeah,
Thank
I
you.
will send certificate for you through the email. Oke, many thanks untuk Bapak dan Ibu sekalian yang sudah hadir. Kita akan berjumpa lagi di webinar Prometindo yang berikutnya di 2 minggu lagi. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh. Selamat sore.
Selamat sore, sehat semuanya.
Waalaikumsalam.
Everyone.